We bypassed the operating system. We parsed network packets in flight. Market data now lives inside our chip, but there is a new trap waiting for the uninitiated. Memory. This is Axiom Tech, and I am Epoch. In this video, we will see this silicon memory architecture. In conventional computing, DDR memory is vast. It holds gigabytes of data. But DDR memory is physically external to the processor. When your algorithm needs to check the current bid or ask price, it must send a request over a physical bus, wait for the memory controller, and retrieve the data. Think of it this way. The CPU is City Hall. DDR memory is a warehouse on the other side of town, and the mayor is your algorithm. When mayor, every time it needs a document from warehouse, a courier must cross the entire city, find the file, and return. In ordinary computing, this is acceptable. In high-frequency trading, waiting 100 clock cycles just to read a single price is not slow, it is fatal. By then, the market has already moved. The opportunity is already gone. Let us be precise about what distance means in this arena. Light travels approximately 15 centimeters in 1 nanosecond. The physical trace between your CPU and DDR memory module is several centimeters long. Before a single bit of data is processed, physics has already stolen nanoseconds from you. Imagine a Formula One pit stop where the fuel hose is 10 meters long instead of 1. The crew is world-class. The strategy is perfect. But the car sits there, waiting as the hose slowly closes the distance. That extra length cost the race. In our world, those extra centimeters of copper traced between CPU and DDR memory cost the trade. The solution here is not a faster courier. The solution is to eliminate the distance entirely. That's mean we have to move the warehouse inside City Hall, to bring memory so close to the logic that the concept of a bus ceases to exist. That is what we are building. The Ghost Trader does not ask permission from external components. We internalize reality. Inside the silicon fabric of the FPGA, only a few micrometers from our execution logic, live dedicated silicon blocks, Block RAM and UltraRAM. These blocks are not measured in gigabytes, they are measured in megabits. But what they lack in raw volume, they compensate with absolute and terrifying speed. Imagine two safes. The first is a massive vault in the basement. Enormous capacity, but a journey is required to reach it. The second is a small safe bolted directly to your desk. Smaller, but you reach it without standing up. BRAM is that desk safe. The ghost does not travel to its data. The data lives inside the logic. To trade, we must know the state of the market at every nanosecond. We need to build the limit order book. This is the live record of every pending buy and sell order in the market. The complete picture of supply and demand, updated thousands of times per second. Software reconstructs the order book using linked lists, hash maps, and pointers, scattered across unpredictable RAM segments. Every lookup is a journey. Every update is a lookup. The data structure is elegant in theory, but physically chaotic. Pointers chasing pointers across gigabytes of external memory. We eliminate the search entirely. We map asset prices directly to BRAM addresses. A flat, parallel array. Price level 100 always lives at BRAM address 100. Without exception. When a new tick arrives from the exchange, there is no search, no tree traversal. The hardware knows the exact physical location of that price level inside the silicon and writes to it in a single clock cycle. They walk directly to room 512. The room number is an address, and the address is the answer. Our order book operates the same way. The price level is the room number. The BRAM address is the door. Speed means nothing without simultaneity. Standard memory has a fundamental bottleneck. You read, then you write. Or you write, then you read. Never both at once. But the Ghost does not accept this constraint. Imagine a single-lane bridge. Traffic flows in one direction at a time. The other direction must wait. Standard memory behaves this way. Read or write, never simultaneously. Now imagine the same bridge, but with two independent decks. One deck carries traffic inbound, the other carries it outbound, both at full speed, simultaneously. That is dual-port RAM. Port A relentlessly updates the state of the market as network packets arrive from the exchange. Simultaneously, Port B continuously reads those exact same prices, feeding them directly into our execution logic. The same memory cell, two independent physical interfaces. We read the market at the exact nanosecond it is updated. Pure, uncompromised parallelism. Two surgeons, one patient, two independent sets of hands, one closing a wound, the other making a new incision, neither waiting for the other. The operating table serves both simultaneously. That is what dual port means inside silicon, and that is why the ghost never blinks. Step back and look at what we have built. A market data packet enters the chip over the fiber optic transceiver. The XI stream parser strips headers in 4 clock cycles. The extracted price is written to the BRAM order book in 1 clock cycle. DSP slices read the updated price and evaluate risk in 1 clock cycle. Execution logic fires the outgoing fix message from packet arrival to order transmission, entirely within silicon. No external bus, no DDR latency, no operating system, no API call. We built the brain, we gave it memory, we gave it reflexes. But a design is only a theory until it is exposed to the brutal reality of verification. Can it withstand a live market replay? Can it handle edge cases, malformed packets, sudden traffic spikes, price gaps? In the next encounter, we simulate chaos. We stress test the ghost against reality itself. This is Axiom Tech, and I am Epoch. I will see you in reality.